Hello everyone. For this tutorial video, I'd like to explain how you can tackle limits of functions with more than one variable as an input. We first start by reviewing what a limit was for single variable functions, which was that if x approaches a specific limit value a from the left and right hand side, and these values are equal, then it follows a limit exists and is also this value. We do this review because it is exactly as true for multivariable functions, but we will see that there are catches/caveats to multivariable limits, which we will see later in the video. The notation for a multivariable limit, such as a limit of a function of two variables, is lim f of x comma y, x approaches a and y approaches b. And there is another notation for it, which is as x comma y approaches a comma b, which is a more condensed version of expressing the same thing. We see graphically a problem with these types of limits is that there's literally an infinite amount of directions you can approach from, whereas with single variable functions there is only two. And we know that limits exist if and only if every path you approach from gives you the same value at the limit point. But before we panic about this, we can remember that we saw in Calculus 1 that when a function is continuous at a specific point, the limit is exactly equal to the function value at that point. And we also painstakingly looked at what functions are continuous and which ones are not. So the same rules and tricks apply with multivariable functions. In particular, if we are given a limit like this, where we have a 3-variable function, we see that all of the functions individually as if they were single variable functions. So treating 3x squared and z separately in the first term, for example, are always continuous. It follows that this overall function and therefore limit is also continuous. Because remember, sums and products of continuous functions are continuous, as well as differences and quotients, provided you do not divide by 0. So now, we can simply substitute in the x, y, and z values given in the limit, and get a finite answer that way. When we do all the computations, we get -14 in total. If we are given this limit for this function, we see it is not continuous throughout its whole domain, but it is continuous at the point in question because the denominator is not 0. So we simply plug in the x and y values given in the limit. We get 5 times 1 over 5 plus 1 is 5/6 as our final value for the limit. For limits that are not continuous at the point in question, we can see that we can use the same tricks from Calculus 1 in some cases as in this example. We factor the numerator and denominator because plugging in the x and y directly gives you division by 0. We see that x minus y cancels out. So now we have it in a form where we can plug in the x and y values, and we get 3/2 as our final answer. The same exact logic from Calculus 1 holds here for simplifying the kind ratio, namely that the simplified version is identical to the original version except that where the discontinuity is. But we know that limits don't care about what is happening exactly at that point, they are only approaches. However, many limits will not exist in a neat algebraic way like that, as this limit shows, because when you plug in the limit point directly, you get division by 0. So the trick is here to take approaches along different lines and see if these lines agree or not, and stop as soon as one line gives us a different value. So we first approach along the line y equals 0, so we plug 0 in for the y's in the function. We get 0 over x to the 4th power plus 0 is 0, the limit of 0 is always 0. In conclusion, the limit along the line y equals 0 is 0, but that is not the actual limit because it is only along one approach. So we test x equals 0 now. We get 0 over 3 times y to the 4th power, which is also 0. The limit of 0 is still 0. Even though we have tested along the basic horizontal and vertical lines, we are still not done because there are an infinite amount of lines we can approach from, so we have to test each one until we get a limit that does not give us the same value. So if we test along the diagonal line y equals x, we substitute in x for y, we get x to the 4th power over 4 times x to the 4th power, which is now a calculus 1 limit, and is 1/4 because the x to the 4th power cancels out. In conclusion, the limit does not exist because the limit along the line y equals x gives us a different value than the previous two limits. Sometimes we will have to take approaches for more bizarre directions rather than perfectly diagonal, perfectly horizontal, or perfectly vertical ones, such as in this example, because we see if we do y equals x on a diagonal line, we get x squared over x to the 4th power plus 1, which is 0 because x to the 4th power increases greater than x squared. And if we choose to use the cubic curve y equals x cubed as our substitution instead, we get x to the 6th power over 2 times x to the 6th power. The x to the 6th power cancels out, we get 1/2 as our limit. And we see very quickly that the limit does not exist, because of the fact approaches from different paths give off different values. Now that we have shown how limits of multivariable functions work, we can use these limits to define derivatives and integrals of multivariable functions, starting with partial derivatives, or derivatives along only one variable at a time. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.